Good evening. I am Tarashankar Debroy from the University Park campus of Penn State. I want to first thank the organizers of PLMSS 2021, particularly Dr. Ashok, Dr. Murthy, and Dr. Solomon. This invitation means a lot to me because I went to school in Durgapur Regional Engineering College and also Indian Institute of Science in Bangalore. Today, I want to focus on the important problems that are faced by additive manufacturing and their solutions using machine learning and mechanistic modeling. More of our work on this topic can be found from my website, my LinkedIn page, and also from my YouTube channel. Topics for today. Additive manufacturing has a number of variants, and we want to focus on three most important ones. And metal printing faces some generic problems. We will review those and see what their solutions are. Many of the issues it faces has to do with the geometry, composition, and microstructural features of the metallic parts. Taken together, this can be viewed as the ability of a process and an alloy combination to print sound parts, and we call printability. The issues of printability of alloys are addressed using physics-based models that we call mechanistic models. So we'll review those. But some problems are very difficult and their mechanistic understanding is still evolving. In those cases, we use data and machine learning to solve problems of this type that are listed here. And based on our current knowledge of additive manufacturing, we want to review what we may rationally expect in years to come. Outlook. There are many variants of additive manufacturing. The three most common ones we are going to focus on, and they are powder bed fusion laser using a laser heat source, directed energy deposition using a laser beam, and also directed energy deposition using a gas metal arc welding torch as heat source. Now there are many common features. All of them use layer by layer manufacturing. Sometimes the layers can be very thin, even thinner than a human hair. And parts with complicated shapes, site-specific chemical composition, or internal features such as internal cooling channels can be made. And most important, this same equipment can be used to produce many different types of components on demand. Obviously, additive manufacturing has many advantages over the conventional manufacturing techniques. And as a result, you will see that additive manufacturing is now being widely used in various industrial sectors such as consumer products, automotive, healthcare, energy, aerospace, and marine industries. Why then only a handful of alloys are printed, and that too mostly by large companies? Several years ago, I put together a team of researchers from national labs such as the Lawrence Livermore National Lab, the Los Alamos National Lab, and industries such as 3D Systems and Rolls-Royce, and universities like Ohio State University and Penn State University to investigate the major scientific, technological, and commercial problems. The details of our findings are available in Nature Materials in 2019, but today I am going to focus on the most important problems. we collected operating data for 3 different variants of additive manufacturing from peer-reviewed recent literature. And we are plotting power, scanning speed. Power varied from little over 100 watts to about 10 kilowatts. And scanning speed, look at the scanning speed on the left here, about 10 millimeter per second to close to 10,000 millimeter per second. And these variations in power and speed results in a great deal of variation of heat input from less than 1 joule per millimeter to about 1000 joules per millimeter. But the most remarkable variation is in the cooling rate. It's less than 100 Kelvin per second to about 10 million Kelvin per second. And because the cooling rate affects microstructure and properties, the variation in microstructure and properties would be astounding. And traditional ways of optimizing microstructure and properties by doing empirical tests throughout this parameter space is not a viable path for additive manufacturing because of the high cost of machines and the feedstock. So we need to optimize microstructure and properties by a path different from how we did that for welding and joining by empirical testing, because costs make it prohibitive to do it the traditional way. We need a new path. So we reviewed the basic problems, but how do we solve them? Many of us here are metallurgists or material scientists, and we study the relation between process, microstructure, property, and performance. But the difficulty here is that this study cannot relate process variables to product attributes like geometry, composition, structure, and properties. So what do we do? In cases where we understand the process adequately, we use the laws of physics to correlate process variables with product attributes. But additive manufacturing is relatively new in the world of manufacturing, and therefore some of the mechanistic understanding is still evolving. So in those cases, we use data to correlate the process variables with the attributes of the products like geometry, composition, various microstructural features and properties. So we are going to be focusing on mechanistic models and machine learning for the rest of this talk. If we want to use a physics-based model to solve geometry, composition, or microstructural features, we need the temperature fields in the entire domain as a function of time. How do we get that? By solving the energy equation. And also, during additive manufacturing, when the heat source interacts with metallic material, it forms a liquid pool. And in this liquid pool, liquid metal moves around and carries heat with it. So we need to also understand the velocity of the liquid metal because it carries heat with it. And how do we solve the energy equation and momentum equation? We discretize the equation. We form linear equations from the differential equations. We subdivide our domain into small parallelepipeds. Let's say this domain is divided into 250,000 cells. And what is it we are solving? We are solving 3 components of velocities, pressure, and enthalpy or temperature. And total, we will have 250,000 cells and 5 equations for these 5 variables. So we'll be solving 1.25 million algebraic linear equations. And if we take about 100 iterations to solve these, we are looking at 0.125 billion equations or 1/8 of a billion equation per time step. If we solve it for 1,000 time steps, we will be solving 125 billion total linear equations. How long does it take for an inexpensive computer to solve 125 billion equations? Well, today's laptops can solve about a billion equations in half a minute. So you are looking at about an hour, and after that you have got all these 5 variables as a function of time for a given set of process parameters and material properties. And we can get temperature and velocity fields as a function of time, and solidification parameters, and a whole host of other things that will become clear as we go on. This figure shows a transverse cross-section. A cross-section perpendicular to the direction of motion of the heat source. And what we see is that liquid metal flows from the middle of the pool to the rim, turns around and goes back. So a temperature field and velocity field is established both during welding as well as during additive manufacturing. Typical velocity in the additive manufacturing pool is between 50 and 300 centimeter per second. And this compares with the Olympic 100-meter sprint velocity, which is typically about 10 meters per second. So the velocity is lower than the 100-meter sprint in Olympics, but is considerable in terms of its ability to transport heat from the middle of the pool to the rim, and having a temperature distribution that we see here for a gas tungsten arc welding pool, where these dashed lines show the path of movement of the liquid metal and the colors show temperature field. Let me see if I can animate it so that we can see it better. This is half of a pool because of near symmetry. Right in the middle, the liquid metal is going to the rim and turning around. There are two loops near the surface. These we call Marangoni loops. They form because of the spatial gradient of interfacial tension, which is a stress. And also there are two loops down below. And these patterns are happening because of the electromagnetic force field that is driving the flow. So there is a temperature field established and a velocity field established during additive manufacturing. During additive manufacturing and welding, most of the heat is carried by the liquid metal within the melt pool, and therefore the flow of liquid metal affects the shape and size of the fusion zone, and therefore the build properties or weld properties. If we ignore the flow of liquid metal, then of course our temperature calculations would be completely wrong, because the majority of the heat transfer occurs by convective flow. And look at the variations of the fusion zone shape. It can be a bracket or a W or a hemisphere, depending on Prandtl number and Marangoni number. This is well known in the welding literature, but right now there is increased interest because of the need to simulate fusion zone shape and size in additive manufacturing. But convective heat transfer is often the main mechanism of heat transfer in the molten pool. And also sometimes a small amount of surface active elements like sulfur, selenium, tellurium, oxygen, they can affect the flow pattern, like 20 parts per million in a steel versus 150 parts per million in steel can reverse the flow pattern from 20 parts per million to 150 parts per million. Now, when the flow pattern is in the middle going downward, it acts as a thermal drill. And so we get a deep pool and a narrow pool. When the liquid metal flows from the middle to the periphery or the rim of the molten pool, then we get a wide and shallow pool. So fluid flow is very important in additive manufacturing. Here is a simulation of wire arc additive manufacturing. The material is H13 tool steel. Current is 200 ampere, 22 volt, and the speed of heat source is 5 millimeter per second. And this part is blown up here, and we see that under the heat source, which is here, the liquid metal is depressed, and the depression results in pushing back the liquid behind the pool. So we have the track that is elevated compared to the original base plate. And we have recirculating flow of liquid metal, and we can get temperature time history at any location from this simulation. For the same process and the alloy, we show different cross sections of the deposit, and we can see that under the heat source, the liquid metal is depressed, and the displaced liquid metal goes behind, forms a hemisphere, and the flow pattern changes and the temperature changes. So at different locations, the temperature experience, temperature versus time thermal cycles are going to be different at every point in the deposit. The same simulation, but we are looking at longitudinal planes. And we can clearly see the depression under the arc, and then the liquid metal that is displaced goes behind and forms the track, and this is another plane, little bit offset from the middle, and we see a similar behavior. But what is important here is that at every point in this three-dimensional part, the thermal cycles and the cooling rates are different. And this difference can sometimes result in differences in microstructure and properties locally. Model predictions must be verified. So here we do just that. For stainless steel 316, we look at the cross sections for PBF-L, DD-L, and wire arc DD. And I must warn you that the scales are different for these three. This is only 0.31, 1/3 of a millimeter. Here it is about 1.4 millimeter for the same length, about the same length, and here this is 2.8. So this pool, which is for DD-GMA, is much larger than the pool that is for DD laser, and this pool is bigger than the powder bed fusion pool for typical operating conditions and for the same alloy, here stainless steel 316. And the reasonable agreement between the predicted and the experimentally determined cross sections tell us that the model predictions are reliable. Similarly, we sometimes implant a thermocouple and take the thermal cycles a little bit away from the fusion zone in most cases, and we see that for different thermal cycles representing different layers of deposition, the models, once they have been validated, are pretty reliable to calculate other parameters such as the cooling rate. And here we are looking at the effect of heat input on the cooling rate for directed energy deposition, and the alloy is H13 tool steel. And we can see that the cooling rate can change significantly if the heat input changes. Many of the metals that we use in additive manufacturing contain volatile alloying elements, and the temperatures in the molten pool sometimes are very high. As a result, many of the volatile components are lost in significant quantities. In fact, composition of the final build is often different from the composition of the feedstock. And the composition change depends on local temperatures, vapor pressure of the alloying element over the alloy, surface area, molten pool volume, and scanning speed. And because we can determine the surface area and local temperatures, and we can calculate the vapor pressures, we can determine the local flux of volatile components at the surface of the molten pool. And it depends on the partial pressure of the alloy, the molecular weight, and temperature, and a coefficient gamma, which is always lower than 1, and it's sometimes called accommodation coefficient. And this process has been used in a model to calculate for different types of commercial alloys the loss of alloying elements. For example, in titanium 6 aluminum 4 vanadium alloy, we lost about 0.9 weight% out of the initial 6 weight%. For other commercial alloys, there were also some significant amount of loss. This figure shows little more details about how these calculations are done. We start with the temperature field on the surface, and therefore from the temperature field, using a model, evaporation model, we can calculate the local flux of all the alloying elements, and using those and the volume of the pool and the surface area of the pool, we can calculate the loss of alloying elements, and by conservation of mass, we can recalculate the final composition of the alloying elements. An important contributor in this is the surface to volume ratio. If the surface to volume ratio is very small, then of course the composition change will be also very small, because the elements lost by vaporization is coming from a larger volume of liquid metal. If, on the other hand, the surface area is large and the volume is low, then of course composition change would be pronounced. So in powder bed fusion, for example, the surface to volume ratio is pretty large because the pool volume is very small. So we see a much more pronounced change in composition in PBF than in directed energy deposition processes. So mechanistic models can predict composition change pretty accurately. Once the transient temperature field in all locations of a three-dimensional build are calculated using a mechanistic model, they can then be used in other models to understand microstructural features. Here we are comparing the numerically simulated grain structure in a directed energy deposition single layer build of Inconel 718, and we are comparing that with experimental results on the left here. And both the orientation of the grains and the size of the grains, they are in reasonable agreement. Also, the morphology of the grains, equiaxed or columnar, depend on temperature gradient and solidification growth rate, and both of these can be computed from mechanistic models. It's not limited only to a single layer deposit. Here we show similar calculations for a 10-layer build, and the computed grain orientation and size compare well with the experimental data. Also, the mechanistic models compute cooling rates, and using those cooling rates and empirical relations available in the literature, we can predict simple features of microstructure. Like here, we are looking at the correlation between secondary dendrite arm spacing and the cooling rate. And if we compute the secondary dendrite arm spacing for various laser powers, they seem to agree well with the experimentally determined secondary dendrite arm spacing. So if we also change the laser power, higher power means slower cooling and therefore larger secondary dendrite arm spacing. So both qualitatively and quantitatively we can understand simple features of microstructure from mechanistic models. We are also trying to use the results of mechanistic modeling to predict simple mechanical properties like hardness. So first step, of course, is to solve the Navier-Stokes equation and energy equation to get thermal cycles, integrate the thermal cycles with the kinetic data for transformation. In this case, we are doing this for a H13 tool steel in which during deposition of successive layers, materials are tempered. And because we know the tempering kinetics, we synthesize the tempering kinetics with the thermal cycles at all locations, and therefore we can predict the hardness for different conditions of deposition. So, synthesis of the theories of transport phenomena and phase transformation provide a very powerful alternative to empirical trial and error. And tailoring of microstructural features and properties is within the reach of the additive manufacturing community. Before we finish our discussion on lack of fusion defect, I want to point out that mechanistic models have been used for understanding lack of fusion defects. For example, both the effects of process variables as well as alloy properties determine the size and shape of the fusion zone. So if we have a multi-layer, multi-track deposit, the gaps between layers and adjacent hatches determine the lack of fusion. And those calculations can be done for different powers, for example, and larger powers will mean a bigger molten pool, and bigger molten pool would mean less lack of fusion defects. So experimentally, it has been found that the predictions of the lack of fusion defect from geometrical considerations using mechanistic models can accurately predict lack of fusion defects. Presence of large amounts of residual stresses is an important issue in additively manufactured parts. And since mechanistic models can give us very accurate three-dimensional transient temperature fields, these data can be fed to commercial codes like Abacus or ANSYS to provide very accurate calculations of residual stresses and distortions. Here for stainless steel 316, we are comparing the residual stresses computed by this hybrid process in powder bed fusion and two directed energy deposition processes. And we find that in directed energy deposition GMA, the longitudinal residual stress is considerably more than in the other two processes. We can also compare different alloys for the same processing conditions to see which one is more susceptible to distortion and residual stress, and those calculations are also much more accurate than doing it simply by the commercial codes, because most of the commercial codes like ANSYS and Abacus do not take into account the flow of liquid metal inside the pool, and therefore the temperature fields computed by the commercial codes are not as good as they can be. So mechanistic models are very useful to support many of the commercial codes. So far, we discussed the applications of physics-based mechanistic modeling to solve problems of additive manufacturing. We correlated the process variables and thermophysical properties of the alloys with some important attributes of the printed parts. The attributes included the geometry, the chemical composition, and some aspects of the microstructural features. In each case, the basis for the correlation was the knowledge of the underlying physical processes, because it is those physical processes that we quantified using the laws of physics. In many cases, we do not have the knowledge of the underlying physical processes, and therefore we cannot develop a quantitative correlation based on laws of physics, because we simply do not know the process to quantify. In those situations, we use available data to correlate the process variables and thermophysical properties with the attributes of the product that we seek to understand better. And the framework that allows us to do that is machine learning. Machine learning also allows us to develop a hierarchy of the important variables. We are going to be discussing several such examples next. Cracking of additively manufactured metallic parts is a persistent problem, and it occurs by multiple mechanisms, depending on the process parameters and alloy properties. I have listed many of those here, such as the laser power and scanning speed, but if I count the total number of variables, I find 12 variables. So if I wanted to investigate this problem experimentally, I will need 2 to the power 12 or 4096 experiments using a two-factor design of experiments. And this is very expensive and time consuming. So if we look at the peer-reviewed literature, we find that the cooling rate during solidification is often mentioned because it determines the scale of the microstructure, and the ratio of the temperature gradient to solidification growth rate determines the morphology, which is often tied to cracking. And during solidification, in the initial phase, the solid fraction is low, and so the liquid can be transported to the two-phase region and can relax the two-phase region. But towards the end, the high solid fraction obstructs the free transport of liquid to the crack site, and therefore the ratio of the vulnerable and relaxation times are also found to be a causative variable in the literature. And of course, everything depends on the solidification stress. So if we take these 4 causative variables instead of all the raw variables, I get 4 mechanistic variables that are related to cracking. So in order to analyze this problem based on these 4 variables, we will need 16 data points following the two-factor design of experiments. And these parameters can be computed using a heat transfer and fluid flow model. CSI, or crack susceptibility index, is correlated with values of these 4 parameters that are obtained by running a heat transfer and fluid flow model. And using the data set of over 100 cases, we can develop a correlation between crack susceptibility index and these 4 variables. Using a linear regression, the higher values of crack susceptibility index means the higher probability of a sample developing cracks. Also, if we look at the hierarchy of these 4 variables, we find that the solidification stress is the most important variable, and the least important variable is the cooling rate. we have a set of more than 100 data points. Each data point includes a set of process variables and also calculated value of the cracking susceptibility index. And we plot them in this diagram where we have the serial number of the data 1, 2, 3, 4 until about 104 or so for all these alloys, and for each of the data we have a computed cracking susceptibility index using the equation that we just showed. And we are now plotting each data. So we have a crack susceptibility index, CSI, and a serial number. These red colored points that have higher cracking susceptibility index had cracks. And the blue ones, we did not detect any cracks. This plot considers various alloys and different printing conditions, and the CSI is very user-friendly and it is verifiable, because if the cracking susceptibility index CSI is higher than about 0.5, we actually observe cracks. And it is computed from 4 mechanistic variables. And process variables are related with cracking data via a mechanistic model. The CSI is very user-friendly and people can use it in the shop floor. We can also produce maps in which we can correlate the raw variables, which is what we have to deal with on the shop floor. So here we plot laser power and preheat temperature, and we plot different contours of CSI. If the CSI values are much lower than 0.5, we expect that these samples will not crack. So maps of this type, we can select conditions to avoid cracking. Using machine learning, residual stress is an important problem in additive manufacturing. And reduction of residual stress can be achieved by using machine learning. Now, we have already discussed that mechanistic models can also calculate the residual stresses for a given set of raw input variables. What's the problem with that? Well, most of these residual stress mechanistic calculations are very time consuming. For a modest size samples, it is not unusual for a simulation to take days. And so if we can reduce the time necessary for using those models, then it can perhaps be used on the shop floor. So what we are doing here is that we are taking all the raw variables and developing a neural network that has the data for 3 alloys, stainless steel 316, Inconel 718, and 800H. So it uses input variables as power, speed, substrate thickness, substrate preheat temperature, and a wide variety of alloy properties. And we take a set of 194 sets of data to train our neural network. And then having trained it, we test it using 49 sets of testing data. And what we find is that the neural network can actually predict the calculated stress values. For each set of data, we use Abacus to run and give us the maximum longitudinal residual stress, and then we develop a correlation between the maximum longitudinal residual stress and the raw variables. So here we are plotting the predicted residual stress by machine learning and calculated stress by mechanistic model. So this is our prediction from Abacus. So when we calculate the maximum longitudinal residual stress computed by a mechanistic model, that means in this case Abacus, with the results of the neural network, the neural network is as good as Abacus, except it doesn't take days. It takes only a few seconds to give you the residual stress values for a given set of raw process variables. Machine learning also allows us to ask which variables are more important and which variables are less important. So we take all of these variables like preheat temperature, power, substrate thickness, scanning speed, and several of the thermophysical properties or mechanical properties like yield stress, Young's modulus, thermal expansion coefficient, and so on. And then we use a random forest model to determine the feature importance. The preheat temperature is the most important variable. If we look at the properties, like here, sigma is the yield stress at room temperature, whereas E is the Young's modulus, then the thermal expansion coefficient or thermal diffusivity. They are kind of equal in feature importance more or less. But if we want to reduce the residual stress and we have one variable to deal with, preheat temperature is the most important variable. Machine learning can also reduce lack of fusion defects. What we are showing is infrared camera measurement, and then we take the periphery or the rim of the fusion zone, that's here. So if we plot it as a function of theta, where theta is the angle from the location from which we are looking at it, the radial distance versus angle theta has a plot like this, and depending on the shape of this plot, we can have a classifier in which we can relate this shape with the presence or the absence of lack of fusion. So the boundary for that separation is this red line. So above this red line, there is no lack of fusion detected, and within the left side of that red line, we have different cases of lack of fusion. We take a few points, section it, and actually observe whether or not there is lack of fusion. So this is also a very effective way of reducing lack of fusion. So far, we have discussed mechanistic modeling and machine learning. And if we look at the different steps we take to actually make and qualify a part, ranging from product design to process planning to production monitoring and control to defects to microstructure properties, inspection and performance, mechanistic modeling and machine learning are invaluable in aiding all of these processes. If you follow the lines for machine learning, it helps practically every aspect of the additive manufacturing process. And mechanistic models can also help in many of these steps that we have identified here. There are many very powerful software for using machine learning that comes with extensive manuals and examples. We have also included the source where one can freely download those and where they have been actually used. So I took this table from our recent review, and it has the applications of these softwares and it has the source of these softwares. So what is in store for us in the coming years? I think many of the problems that additive manufacturing faces is going to be solved in the near future. But it's not going to happen following the same path that we adopted in the past to solve problems of welding and casting. It is because empirical testing in the case of additive manufacturing is very expensive, and it's impractical because of the large parameter space that we discussed earlier. Additive manufacturing is going to be adopted in diverse industries in the future, and my evidence for that is the trend of sale of commercial equipment and the revenue growth. So I think it is going to be more widely used in the near future, and it will also contribute to the knowledge base of metallurgy. Metal printing is also generating an awful lot of new knowledge. So it is going to be a two-way street where it gets support from a mature and rich knowledge base of metallurgy, but it also contributes to the knowledge base. And we are going to be able to print more alloys, and as we solve most of the problems of additive manufacturing, small and medium businesses will get in the act, and they are the ones that generate a lot of jobs. So this is really a good news for additive manufacturing. And finally, the reason I think it will grow faster than we think is because of the rich knowledge base of metallurgy and the emerging tools. Mechanistic modeling and machine learning will expedite the development of additive manufacturing. So thank you very much for listening. And if you have any questions, I'm going to be here. Thank you again.